Hi everyone, my name is Zhixu. I will introduce our new work on rethinking normalization methods in federated learning. This work is together with Jingwei Sun, Ang Li, Pingyu Chen, Jianyi Zhang, and advised by Professor Hai Li and Yiren Chen. Batch normalization is one of the most important concepts in deep learning. It was designed to solve the internal covariance shift problem. Internal covariance shift describes a phenomena that during the training of deep neural networks, each layer's input distribution varies due to the parameter changes of preceding layers. Such an issue requires the internal neurons in a given layer to adapt to the varying input distributions and hence slows down the convergence of model training. Internal covariance shift has been well studied in the centralized learning scenarios, and an effective approach to mitigate this issue is batch normalization. Batch normalization is one of the key reasons that enable us to train very deep neural networks like ResNet 56 or ResNet 101. Although batch normalization has achieved a great success in deep neural network training, it actually harms the federated training. Here we show our experiments on a small CNN model trained on Silverton dataset. The architecture of the CNN model is shown on the right-hand side table. We can see from the figure on the left-hand side that there is a non-negligible degradation on the performance of batch normalization. The algorithm we used in these experiments and all our following experiments is FAT-ABG. This phenomenon has been spotted in several previous papers. However, they merely attributed the performance degradation to the non-IID setting. In this paper, we should provide a focus and analysis on the problem and make efforts towards understanding the phenomenon. A natural question is, why don't we just discard the normalization module? The following slides we will provide some insights that normalization module is actually important. Finally, we should provide possible substitutions of the batch normalization. Including batch normalization, there are a bunch of normalization techniques that are proposed. We categorize them into one big family, namely activation normalization. The most famous activation normalization techniques are batch normalization and layer normalization. The image here credit to the internet. We can see from the image that batch normalization is normalizing each channel across a mini batch, while layer normalization is normalizing across channel of each sample. All these activation normalization techniques can be written in one formula, which is shown on the right. Different techniques compute mu and sigma differently. Batch normalization uses mini-batch mean and mini-batch variance as mu and sigma, while layer normalization and group normalization use mean and variance across channels or features of one data sample. Given the formula in the previous slides, the activation normalization techniques have the scale invariant property. Here we have the formula too, where W is the weight parameters of the preceding layer, H is the input to the layer, and A is a non-zero scalar. Here we can see that the normalization results won't change if we magnify the weights of preceding layer by a non-zero factor A. The same also applies to layer normalization. If we check the backpropagation, we can see that normalization layer has an auto-tuning effect on learning rate. That is, if the weight AW is large, then in backpropagation, the gradient will be shrinked by a factor of 1 over A. On the other hand, if AW is small, the gradient will be enlarged by a factor of 1 over A. Given the scale invariant property, we can easily prove the following lemma that asserts that for any function that has the scale invariant property, that the gradient of that function at some point w is orthogonal to that point. The lemma is proved by differentiating against the lambda, and we shall skip the detail here. Together with the updating rule shown on slides, we derive the equation 5. The auto-tuning effect in previous slide will enforce the norm of weights to converge to an equilibrium, where in the equation 5 the norm of weights is large, then the norm of gradient will be small. This property is important to federated learning. In this slide, we will introduce external covariance shift. In federated learning, participating devices train their local models for multiple steps in each communication run with their own private data. In this process, we observe that the statistics of channels is significantly diverse across devices. This phenomenon is caused by the independent local training process on different devices, resulting in different internal covariance shift. We name this phenomena as external covariance shift, which is a unique problem in federated learning. The external covariance shift phenomena slows down the convergence of the global model in federated learning, since the feature distribution varies after aggregation and neurons have to keep adapting the updated feature distribution. We attribute this feature distribution shifts as a key reason that batch normalization drops the global accuracy, which will be detailed later. In this slide, we shall illustrate why the weights equilibrium is important to the federated learning by a toy example, and this also supports that we cannot drop the normalization module in federated learning. For simplicity, we use a fully connected layer as an example for analysis. Note that such an analysis can be naturally extended to other types of layers. Specifically, a FC layer is represented as y equals to wx plus b, where x is the input to this layer, w and b are weights and bias, y is the feature of this layer. For two sets of W1 and W2, if their feature deviation have significant discrepancies, that is to say the sigma of Y2 is far larger than the sigma of Y1, then we can derive that the norm of W1 is far larger than the norm of W2. Thus, the essence of external covariance shift describes the shift of model parameters norm, which harms the aggregation. The scale invariant property inherited in batch normalization and layer normalization is able to alleviate the obliteration problem in aggregation caused by external covariance shift. We have demonstrated that the batch normalization and layer normalization can automatically tune the learning rate of the weights of the previous layer. Consequently, the norm of weights will reach certain equilibrium, and this process is regardless of the input distribution. Formally, we iteratively apply the updating rule. We can see that where W0, we can see from the equation 7, the W0 is the initialization. We have the norm of gradients will be similar since otherwise the auto-tuning property will automatically magnify or reduce the norm of the weights. The adaptive balancing property makes a normalization module indispensable in federated learning. We explain the fail of batch normalization by the length of external covariance shift. We train two identical models from the same initialization with two local training datasets in a federated learning round with IID data. The distributions of each layer's feature is shown in the figure. The data of two local training datasets are the same except having different mean values, which can be easily normalized by batch normalization. The results show that two devices have totally different feature statistics from the same channel, with training from the same initialized model. For the second and third layer from the figure, the input distributions are normalized to similar statistics, but the output channels still show a significant statistical discrepancy. Due to external covariance shift, model neurons have to adapt to new input distributions after aggregation. This is caused by different input distributions by the corresponding neurons on other devices. After applying batch normalization, different devices will have varying running statistics, and the central server cannot obtain correct running statistics by simply averaging local statistics. Wrongly obtained batch normalization statistics that mismatch feature will lead to information loss or introduces extra noises. Given the failure of batch normalization, layer normalization becomes a good choice of the normalization layer in federated learning, since layer normalization normalizes across channel in a sample-wise manner. It does not suffer from the statistic discrepancy across devices. Further, layer normalization possesses all the advantages discussed above. Empirically, we show the experimental results on CIFAR 10 with VGG 11 and ResNet 18, and on CIFAR 100 with ResNet 18. All experimental results demonstrate the overwhelming performance of layer normalization against batch normalization. For the additional experiments, we show in left-hand side that normalization techniques have effects on the magnitude of weights, which empirically verifies the auto-tuning effect on magnitude of weights. Models trained with normalization techniques have smaller gaps on magnitude of weights with that of models trained in centralized manner. On right-hand side, we show that the averaged discrepancy between different clients' feature distribution where layer normalization achieves the lowest average distribution discrepancy. The distribution discrepancy is approximated by 2 versus-side distance. Thanks for your attention. Our code can be found at this link here.